I just want to do a quick little conversation about buffers. This was done earlier in another chapter, but I thought I'd do just a little thing about buffers here because it's not about acid bases in general, just particularly just about buffers. So here you go. Buffers is just a solution, well, a buffer is a solution of a weak acid with its conjugate base. I have an example right here of HNO2 and KNO2. They differ only in the H. The K is there, but the K goes away. Remember that spectator ions, ionic compounds dissociate in water. The spectator ion is there, but he's not really doing anything. And that's the K1 positive. So KNO2 is really NO21 negative. So we have HNO2 and NO21 negative. You recognize that's a buffer already. You have to see that as a buffer. They only differ by H positive. Buffers are both. They intimidate the snot out of students up front, but once they get used to it, they like seeing buffers because the pH calculation is actually easier. So basically, recognize buffers because they are both. The way you're going to calculate the pH of a buffer is you could do it because it's weak acid and a conjugate base. You could focus on the fact that it's a weak acid and use this equation up here. And instead of A negative being just the concentration of H3O positive, there's this plus X thing that's going on. And the calculation is a little bit different. But if you work through all of it and keep on going and you say, hey, you go from here to that, hey, you end up with this wonderful little equation, pKa equals pH minus the log of A negative or HA. We always rearrange that. Don't get caught up in that just yet. But realize it's all coming out of a weak acid pH calculation, which you've done a lot of. You're rearranging the weak acid by taking the negative log of both sides. Right here, you just take the negative log of both sides. Negative logs are really P, so that's why it's becoming pKa and pH3O positive. Rearrange that, and what you get is this thing called the Henderson-Hasselbalch equation. Whoops, missed an L there. In this equation, pH equals pKa plus the log A negative over HA. You just substitute in the given values, and you go, and you have the pH. It's straightforward. The only thing that students forget about is this ratio here. They forget which is on top. And I would say, hey, A negative is the base, HA is the acid, and you always sit on the acid. Your acid is your bottom. So focus on that the acid is the bottom, and you will never forget it. I have two little example problems. One, hey, look at this problem. pH of 100 mils of an acid. Do you have both? No, you just have one thing. So that is just an acid. So the way you would calculate that is down here by the using the Ka equation, solving for X, plug that in, get the pH. That's a weak acid problem. Not repping weak acids right now. I just wanted to show you it because all it contains is one thing. The buffer contains two things. You have the acetate along with that acid again. You have two things present. So you have a buffer. A buffer is both. So use the Henderson-Hasselbalch equation and plug in and go. You have to recognize that acetate is the base. Acetic acid goes in the bottom. One thing I would like to point out to you is in this substitution of the concentrations, not in this particular example, but in other examples, you'll find that these volumes may or may not be necessary. If you notice there, the 40 mLs is canceling out the 40 mLs. So you can not include it and just focus on the millimoles. Later on when we do titrations, all you're going to have is the millimoles, and I'm saying you don't have to calculate it into a concentration because the volume numbers cancel out. The buffers are easy. Buffers are both. Just plug it in the Henderson-Hasselbalch equation and roll with it. Have a great day.